Hello students, in this video we'll discuss several matrices that have the same singular values as the underlying matrix given. So let's be given an m by n matrix A, and we recall the singular values of A are the square roots of the eigenvalues of A transpose A, right? And so, of course, A transpose, of course, what will this be? So, of course, A transpose is going to be an n by n matrix times an m by n matrix. So the result is going to be an n by n matrix over here, right? And so now the idea is that we're going to write down these singular values like so. So in other words, the singular values of A are always written like this, for sigma 1 bigger than or equal to sigma 2, all the way down to sigma r. That's the last non-zero singular value, right? And that's bigger than or equal to sigma r plus 1, all the way down to sigma n, right? And the typical assumption is that these terms over here are 0, and that r is the rank of A, so r is the rank of the matrix A, which is the same as the rank of A transpose A, right? Okay, so those are the singular values of A, and so now we have a couple propositions of these things. So the first proposition we have is the following. It gives us a determinant relationship over here. So here's our first proposition. Proposition is that the absolute value of the determinant of A is equal to the product of the singular values, sigma 1 through sigma n, right? And in this case, we're not going to assume, because if any of the singular values are equal to 0, then this product is going to be 0. So in this case, let's assume that sigma 1 through sigma n can be arbitrary, and they don't necessarily have to be equal to 0, right? So typically we assume that these things are 0. That forces the rank to be 0, but in this case, it's always the case that this is true, right? And so the proof of this goes by the actual singular value decomposition, right? So the proof is by the SVD, by the singular value decomposition. We have that A is equal to U sigma, the matrix of singular values, right? And of course, this is going to be what this sigma matrix over here is going to be an m by n matrix over here, and then V transpose over here, right? And so U and V are orthogonal matrices. So U and V are orthogonal, meaning that their transposes are their inverses, right? So now I can use this formula over here. And of course, this is the case when A is a square matrix. So when A is a square matrix, this is going to force M to be equal to n. And so this matrix over here is really an n by n. And all these things are just n by n matrices over here, right? So when A is square, this forces, of course, A to be an n by n matrix, right? In general. Okay, good. And so now let's compute the determinant. So the determinant of A is the determinant of U sigma V transpose. And now by properties of the determinants, this is just going to be the determinant of U times the determinant of sigma times the determinant of V transpose. Okay? But of course, since these are orthogonal matrices, we know the determinant of orthogonal matrices are plus or minus 1, right? So this is going to be plus or minus 1 times the determinant of sigma, right? And that follows now that the determinant of A, an absolute value, and the absolute value of the determinant of A is just going to be sigma 1 through sigma n, right? That gives us a proof for this determinant relationship. So first, this first proposition assumes the matrix A is square. Now these other propositions will not necessarily assume that the matrix is square, but they give us other results. So here's the next proposition we'll prove. Proposition, let's call it proposition 1, proposition 2. So it says that if phi is a m by m unitary matrix, orthogonal matrix, then the singular values of phi A are the singular values of A. Okay. And the proof of this proposition is actually just one line long, right? Because what we can do is if I look at this matrix over here, phi A, right? The singular values of phi A are the eigenvalues of phi A transpose with phi A, right? which is equal to A transpose phi, A, which is just A transpose A, and that gives it to us. In other words, the eigenvalues of this matrix over here are equal to the eigenvalues of that matrix over there. So in other words, they have the same singular values, right? Because if I take the square root of those eigenvalues, it's the same as the square root of those eigenvalues. So that's great. So in other words, if I multiply a matrix by a unitary matrix, it doesn't change the singular values at all. And then finally, the last proposition is that that says that if A is positive definite, then this implies that every eigenvalue is a singular value. Every eigenvalue is a singular value. The eigenvalues and singular values are the same. Then eigenvalues of A are the singular values of A. Okay. Now the whole point is that positive definite matrices are automatically self-adjoint, right? So if I have an eigenvalue, so if AV, so proof, if AV is equal to lambda V, right, then this implies that A transpose A V is A transpose of lambda V, which is lambda A transpose of V, right? And I know that the eigenvalues of A transpose are the same as eigenvalues of A, right? So this says that A transpose A V is lambda squared times V. In other words, the spectrum of A transpose A is just the spectrum of A, everything in the spectrum of A, quantity squared like that, right? So in other words, if I take the square root of an eigenvalue of A transpose A, I just get an eigenvalue of A. So that says that if A is positive definite, the eigenvalues of A are exactly the singular values of A. So in this case, we have several examples of different matrices that if you perform a unitary multiplication of a matrix, a multiplication of a matrix by a unitary matrix, that doesn't change the singular values. And if you have a positive definite matrix, then the eigenvalues of the positive definite matrix are the same as the singular values of the matrix in question, right? So these are two very sort of important basic properties which help us study singular values for very special types of matrices. Thank you very much.